breaking this up into two pieces. Section 8, chapter 8 is set theory proofs. So we kind of scaffolded, we built this in 3 different ways. First section was proving an element lives in a set. That was our first thing. So you should be able to prove that an element lives in a set. And we did a lot with set builder notation in this section. So you should be comfortable with set builder notation here. 8.2, proving one set is a subset of another. So that was the second piece that we were building in 8.2, proving that one set is a subset of another, both with set builder notation and with like intersection and union and cross product and all that stuff. So both types of proofs in this case. And then section 8.3 was proving that 2 sets are equal. So proving 2 sets are equal in section 8.3. Again, we've got 2 different types of proofs here. We can do these with elements. So remember, you can let an element live in the left-hand side, show the element has to live in the right-hand side, and then you have to do it the opposite way also, right? Assume an element lives in the right-hand side, show it has to live in the left-hand side. So that, and we also had a couple of set theory equations. We didn't do a ton with those, but set theory equations are another way to prove that 2 sets are equal. That comes up more in discrete. If you are interested, we do a lot with that in discrete. All right, that was chapter 8. Section 9.1 was the only thing we did from chapter 9. So that is disproof by counterexample. So remember, 2 steps in a disproof by counterexample. You have to find me a counterexample, and then you have to demonstrate that your counterexample works. You got to do both. So you can't just write down the counterexample on the piece of paper. You have to walk your reader through the concept of why your counterexample actually works. That was it from chapter 9. Chapter 10 was induction. Basically, you should be able to do an induction proof. That's chapter 10. We've got the base case and we've got the induction hypothesis. We've got in the induction hypothesis, the we know and the need to prove. I guess you should be able to explain how an induction proof works also with dominoes, right? The domino analogy. If I can knock over the first domino, that's the base case. And if I can, whenever a domino falls over, the next one falls over, then I can knock over all the dominoes. So you should have the basic analogy. But in essence, chapter 10 is you should be able to do a proof by induction. You should be able to do a proof by induction. Nothing with strong induction on the test, just weak induction. We read about strong induction, but that will not be on there. Just weak induction, that's all I'm putting. All right, chapter 11 we skipped because of a sad extra week of break and transitioning to online. Chapter 12, so we've got a lot of stuff in chapter 12. You should know the definition of what a function is, definition of a function. And then we've got some other terms in here as well. Domain, codomain, and range. Those were the big terms that we had in 12.1. Domain, codomain, and range, along with pre-image and image. So pre-image and image, those 5 terms. 3 different ways of listing a function, and you should be comfortable with all of them. We can do list of all the ordered pairs, we can do an arrow diagram, or we can do a rule. So you should be comfortable with all of those ways of defining a function, listing all the ordered pairs, an arrow diagram, and a rule. All of those you should be comfortable with. Definition of 2 functions being equal. So definition of 2 functions being equal. And again, if 2 functions are not equal, you should be able to come up with a counterexample there. 2 functions being equal. And then if I give you an example, you should be able to decide whether it is or is not a function from those 3 things, from an arrow diagram, from a set of ordered pairs from a rule, deciding whether something is or is not a function. Okay, 12.2, injective, surjective, bijective. You should know all three of those definitions: injective, surjective, bijective. Those are definitions that you should know. And then in essence, in this section, we have prove or disprove for injective, surjective, and bijective. So if I give you a function, you should be able to prove whether it is injective, surjective, bijective. I promise that I will not give you ones like on the homework with ordered pairs as input to tell if they are injective, surjective, bijective. Those were fine for the homework where you had a little bit more time to play with them, but that's harder than I would want for a test. So I promise we won't do ordered pairs on the test. It was just in the homework. Remember also, especially with surjective, the scratch work is really, really helpful. Scratch work for surjective in terms of coming up with a pre-image is going to help you out a lot. Okay, 12.4, composition of functions. So you should know the definition. How do you do F circle G and G circle F? How do you do those? And then we had some properties of function composition. It is associative, right? It preserves injectiveness, and it preserves surjectiveness. So remember what that means. If you have two functions that are injective and you compose them, you get another function that's injective. If you have two functions that are surjective and you compose them, you get another function that's surjective. That's the preserves part. And then 12.5 is inverse functions. So you should know the definition of an inverse function, when an inverse function exists, and how to find an inverse function. Definition, when an inverse function exists, and how to find an inverse function. Those are the three things from section 12.5. Okay, that takes us into chapter 13 then. So chapter 13 was cardinalities of sets, right? Cardinalities of sets. You should know the definition of two sets having equal cardinality. Definition of two sets having equal cardinality. You should be able to prove that two sets have equal cardinality. And that means you have to come up with a bijection from one set to the other. And again, we should be able to do this in all three cases. You could do, or you could use any of the cases. Your bijection could be a list of ordered pairs. Your bijection could be an arrow diagram, or your bijection could be your rule. So you can come up with the bijection in all of those possible ways. You do not need to know the proof that the natural numbers and the real numbers have different cardinalities. You should know which sets have the same cardinality and which sets have different cardinalities. So you should know, for example, that the natural numbers and the integers and the even integers and the rational numbers all have the same cardinality and the real numbers don't, but you do not need that proof where we listed all of the elements and then we changed the ith entry, right? That proof you do not need to have memorized for the test. And then 13.2, we've got a definition that started this section: countable, countably infinite, uncountable. So those are definitions you should know: countable or countably infinite and uncountable. Definitions there. You should know common sets and be able to classify them. So like, for example, are the integers countable or uncountable? Are the real numbers countable or uncountable? You should know those common sets that we talked about a lot and whether they are countable or uncountable. You do not need to know the snake diagram of the fractions. Remember, that was where we kind of snaked through on a diagonal, right? You don't have to know that. It's interesting, but it's not something that I need you to know for the test. And you also don't need to know the discussion that we did about the continuum hypothesis and all if not and all of that stuff for the test. Again, that's interesting, but not something that I would necessarily ask you about on the test. So there's some stuff that's just fun, but not a good test question, and that's there. So, and that is the end of the stuff that we covered. So chapters 8 through 13, what questions does the Whirlwind Tour raise at this point in time? Anything? All good? All good? Okay. So then I will send out an email just so you have the details in front of you, but 8 o'clock Monday morning, we don't need to sign in early because there's nothing happening after this and it won't take the whole hour and 45 minutes. It's just a regular test. Once everybody is signed in, I will put the test up on Moodle and then I'll walk through whatever we need to walk through. So probably I would sign into Moodle before you are on Zoom so that you can get it right away when it's on there. All right. Same thing as last time. Also, when you're done, let me know, private chat, take a picture, upload it, and then make sure, please, to stay on Moodle until I acknowledge that I've received your test, or stay on Zoom, I'm sorry. Stay on Zoom until I acknowledge that I've received your test in Moodle and then I can read it and then everything came through. Okay. All right. I'm super glad we did a test earlier in the semester so you don't have all of the stress of how we're going to figure out a Zoom test and during final exam week. So I'm glad we did this once. It's still not ideal, but at least it works. Anything else? Comments on the semester? You're more than welcome to put those in the evals, but anything you want to say at this point? Questions on homework, questions on the Whirlwind Tour, logistics for the test on Monday. Anything? Anything else? No is fine, but I want to make sure you got the opportunity. All good? Okay, all right. Proof notebook due at noon. Proof notebook due at noon. If you haven't submitted it yet, please and thank you. And homework from chapter 13 due at noon on Monday. Look for an email from me, again, just with a summary of what's going on Monday so you have it in your inbox as well. Last call. Anything else before I sign off? All good? Everybody good? All good? All right, cool. Happy studying. I will be on email this weekend if you have questions, and I'll see you at 8 on Monday. Have a lovely weekend. See you guys.